Everyone, welcome to Deep Dive. So this one is a little bit different than previous deep dives. In the past, I've always had a guest, but this one couldn't find a guest, so decided I would just do it myself. And this one also is different because it's not an oracle. We've only in the past had oracles. This one is not an oracle. This one is on Tornado Cash, which we thought would be good because it's kind of very, very relevant. So I'm going to this one, I'll give kind of an overview of Tornado Cash and how it works. And then I'll probably even deep dive into the code a little bit at the end because it's actually really, really short. I don't think I'll be nearly an hour like I am most of them. And then Spuddy is behind you guys on the camera.
Hey.
He'll be asking all the questions that will hopefully make this talk palatable for everyone. So what is Tornado Cash? Tornado Cash is a privacy tool. It is, a lot of people consider it to be a mixer. So you put Ether in, pull Ether out. You can't tell where it came from. So you can change addresses and nobody knows where it came from. The big way, I'll just sort of draw it here. So there's the smart contract, which is Tornado Cash. And then what happens is, so you'll have Alice, Bob, and Spuddy, and they'll each deposit 1 ETH. And they'll place it into this smart contract and then to a bunch of random addresses. So they probably newly minted these things. And then they pull out the ETH. So each of them gets 1 ETH. Now, as you guys can tell, let me pin myself. Okay, so as you can tell, it's all the exact same amount of ETH. The reason is that each one of these corresponds to each one of those people and addresses. And if Alice had 10 and this person had 10, you would probably know with a high likelihood that that is Alice. That's actually, so what they do is they actually just fix it at a deposit amount. So each smart contract actually, so there's a bunch of Tornado Cash smart contracts. Some of them will be for 1 ETH, some of them will be for 0.1 ETH, some of them will be for 10 ETH, and you can go and pick, and there's sort of different liquidity in there. Other things as far as best practices and how it works, you can tell how is sort of anonymity achieved here. The way that it's achieved is because we're all putting funds in and then you can't tell which Ether goes to who. So the more people you get in here, the harder it is to tell where it came from. If Alice was the only one who put money in and then pulled it out, it doesn't work like that. Everybody would know it's her. In the same way, if Alice deposits it and then 1 second later pulls it out, you'd probably know that that's probably Alice who did that. So you want to put it in there and then wait some time before you can pull it out. And that's sort of the best practices of how it works. I think like in a nutshell, that's actually just Tornado Cash. So like if you wanted to stick at a super high level, this is it. It's not very complicated, but what we're gonna do here is get into why it actually is complicated and how this actually works. So we'll work on a deposit. Okay, so Mike, can you hear me too? You're good.
Yeah.
So whenever you place in, we'll just use the 1 ETH example. So whenever you deposit 1 ETH, so it goes like this. So you deposit, but you have to deposit it with what's called a commitment. The commitment here, so in Tornado Cash V1, it's the commitment is just it's the hash of So you have a secret. So you can just pick a random number. That's like, keep it, you know, your seed phrase or whatever. This is your secret. And then what's called a nullifier. A nullifier, again, just you can pick a random number. That's, both of these are kind of secret numbers, but for purposes, we're going to call them different things. So you would input in a commitment with this. And with this commitment, what happens is you deposit it, the smart contract mixture that you transfer at 1/8, and then it takes your commitment here. And then with your commitment, it places it into a Merkle tree. So we'll go over here and we're going to draw Spuddy. Yes.
Does the contract give you the commitment when you go to Tornado Cash, say, because personally Spuddy's never used it. So does it give you the commitment?
Yeah, you can, so like there's scripts that you can run. Like I don't actually, I don't need to, but I've never actually used the front end. So I use the scripts, and yeah, so it can even give you a secret, and it can tell you what that is too. But you might not want to use the automated tools to make your secret.
Okay, so so when you go there, there's automated tools to give you those numbers. You put in your ETH, and you can wait and put them in on the other side, which is what you're getting at now.
Yeah, which and how it is. So there's some other things that you actually have to keep track of whenever you're going to claim it. So you don't just need your secret and then you can go and claim it. Now, because the problem is, so in a Merkle tree, so a Merkle tree is like this, and this will make sense. So we're actually going to look at the code afterwards. So it'll actually make more sense whenever like you're like, why is he going into this? So let's just do like a Merkle tree here. So these are the roots of the Merkle tree, they're called. And this will be like, so like 0x Spuddy. So this will be Spuddy's commitment. This will be Alice. This will be Bob. And this will be Mike. You know, it looks like an address. It's a bytes longer. So bytes 32. And then the next one up. So on the tree, this is the hash of these two. And then at the very top, this is the hash of the bottom, these two. Sort of makes sense so far? So you would just take these ones and hash it and get this, take these two, hash it and get this one. So if you wanted to, whenever Spuddy gets a commitment, what it does is it'll place his commitment in here. We'll say this one was empty. It placed it in here. And then this hash changed and this hash changed. These ones didn't. So now in the Merkle tree, this is where it is. Now Spuddy's commitment is in this Merkle tree. Now what he could do, what you could do, is just kind of like Spuddy asked, like with the secret, you could come and say like, hey, I know the secret and I know the nullifier, give me my ETH. And he could put that in his input and his function and go and claim it. The problem is everybody would see, hey,
oh, you'd see my address called that function.
He knew, yeah, Spuddy put in the same commitment as Spuddy before.
Yeah.
So that doesn't work. How do we actually keep it anonymous here? And so we need to use zero knowledge proofs. And so whenever we place it in the Merkle tree, well, we're actually going to prove with zero cash or with Tornado Cash to make sure that it's anonymous. You're going to prove A, that you know this secret, so then you can get it. So you know the secret and the nullifier, but then you also know, hey, I know it's somewhere in this Merkle tree. And that's actually what the code is doing. So what it's saying is, hey, I know the secret and this one somewhere in this Merkle tree is my commitment. And so whenever you're inputting it, you need to actually keep track of. So like for Spuddies, you would have this whole Merkle tree. You would need to keep track of, so that this root that you're So whenever you deposit it, it actually returns to you the location in the Merkle tree. You keep track of this. You would need to know Alice's as well, because you need to calculate out the hash all the way up. So you need to know this one, this one, this one, this one. So you would keep track of all of those. They're called path elements and path indices in the Merkle tree. So then you would input these as part of your proof. So then you're like, hey, this is whenever I put in my secret and my nullifier, it corresponds to this one in the Merkle tree. And then it says, okay, so now all the smart contract tells, which we'll get into how zero knowledge proofs work a little bit, but basically you're not saying I know the secret. You're saying I know the secret, but you're also saying, and it's somewhere in the Merkle tree, but I'm not telling you where. That's what you're telling it with Tornado Cache, and then it allows you to pull it up. So questions so far on the high level stuff, I guess, before we jump into the code. No. Mike?
Yeah, the zero knowledge stuff is just still a little fuzzy to me.
Freeze.
Can you hear me?
I think I might be freezing. Hopefully this recording isn't bad. Okay. Mike, Owen, any questions?
He asked a question.
I don't even know if I have a question, but I think I'm lagging.
I heard you fine.
Oh,
Okay, so now we're gonna come and we're gonna actually look at some code. Hopefully I'm not too laggy here. The internet might be going in and out.
Well, for your recording, you won't be lagging.
All right, Spuddy says for the recording, it'll be fine. Sorry. Okay, so now I'm gonna share my screen here. And we're gonna get started. Okay. So for sharing my screen, the big thing that you guys should know, so Tornado Cache's code is down. This is a problem. So luckily I have some Tornado Cache code that was already on my computer. We can walk through it, but I am going to update. We're actually not going to walk through it because we're going to walk through a fork of it. And the reason is that in the Tornado core code, I can show you. So down here in the dependencies, you'll see that a lot of these dependencies were actually specifically, so like Circom lib, and they pin various ones. Also, it's super old. So whenever you do like an npmi, it just breaks. Same with running all their tests were broken, basically because a lot of these libraries have changed over time and they didn't actually keep up with it. So Tornado Core is actually broken. We can go over the contracts, but it actually doesn't work anymore if you just wanted to like fork it and run tests or make it work. But this person, Chi-Cheng Liang, who I actually have no idea who they are, they forked Tornado Cache and implemented Poseidon. So Poseidon is the newer hash. It's a newer hash function that's more gas efficient, and they put it in there. And they made all the tests work and updated all of the dependencies. So we're going to use their library because actually the code is exactly the same, everything except for which hash function you're using. So we'll walk through their code, which, like I said, is completely identical to, sorry, wrong repo. Okay, so we'll clone this down, get started. And I'll do PMI. All right, so that's in here, but in Tornado Core, you'll see this structure, and it's actually the exact same as here, minus this one was built. But there's two main structures in the Tornado Cache contracts. There's the Solidity contracts here, and then there's the Circom files. These are the circuits. This is where there's kind of the zero knowledge proofs, the bread and butter. And we'll kind of get into that. So in the Solidity contracts first, The big file that you're actually going to want to know is tornado.sol. So tornado.sol, this is where a lot of the functionality is. You'll see there's the deposit function there. And this just takes the commitment, or I guess we can back up even. So in the constructor, so it takes a verifier. So this verifier contract is here. You'll see it actually is a symbolic link because we have to build it. It's created, not actually as part of the zero knowledge proof process, which we'll get into. The other things you need is a denomination. So this is like 0.1 ETH, 1 ETH. That was the thing that we're talking about. Merkle tree height. That's just how big your Merkle tree is. I think they use 16 for Tornado Cash. I think there's probably pros and cons with relative to gas and storage costs, and then the hasher. So now we're going to be using Sidon for ours, but they use MIMC for Tornado Cash. I know the names are awful, but you can basically just place that in. The hasher, also you'll look and you'll be like, where on earth is the hasher? So in like the Tornado contracts, you'll be like, I don't see the hasher contract anywhere. Where on earth could the hasher contract be? And that's because they actually build it. So you'll see down here in the scripts, it has compile hasher. And that's because it's like a pre-compiled one. So Circom, you can actually do a lot of these pre-compiles that make these Solidity files, and it'll just be bytecodes. There is no Solidity that matches any of this. It's all just bytecode, and it does hashing functions in a crazy efficient way. Which is why I guess I give a shout out now to those guys. So over here, this is the group that makes all the Circom stuff. This is IDEN3. I think they're EF grantees, so Ethereum Foundation supports them. And they do all of the Snark.js libraries. They do anything you're doing with zero knowledge proofs. They're probably behind it in a lot of ways. I'll link to their website. This is their main repo. And you can see here, Jordi Bellina. I've watched this talk like a million times. I think he works at Polygon now. But yeah, he did a lot of the zero knowledge stuff for IDEN, and super great resource. Basically, none of this would be like, you'd have to write your own zero knowledge circuits if it wasn't for those IDEN guys. So if you're wondering where the hasher contract is, you just have to run a script, which is weird when it says, yeah, whenever you're doing Solidity files. I know that took me a super long time to come. So back to the Tornado contract. So after you have the constructor done, you'll see this is a tiny contract. We're like halfway done with it. The next piece is the deposit. So I explained to you guys what the commitment already is. Hopefully you guys understand that. But yeah, all you need is, so process deposit here, that's what it takes your 1 ETH. So it just takes 1 ETH and puts in inserts. So this is inserting it into your Merkle tree. The commitment. The Merkle tree insert, that's this. Somebody else wrote this. I think Tornado like slightly edited. It's just Merkle tree code. So it's a Merkle tree in Solidity. It's nothing special to Tornado Cash. You're just making a Merkle tree and keeping its history. Next, what you're gonna do. So then there's a few more functions. There's just withdraw, which we'll show, and then there's is spent and is spent array to check if you already withdrew. So that's it. But what you're gonna need is you're gonna need a few things. So you're gonna need a proof. So the proof is what we'll get into once we actually go look at the Circom files. That's what you generate using zero knowledge proofs, and that's where you need a bunch of that input. You're gonna need the root. So if you remember on my Merkle tree, this was like the bottom root number of your Merkle tree where your thing is located. You're going to need your nullifier hash. So this is a hash of your nullifier, which you use to make. they're gonna verify that that matches, so your nullifier needs to match. And then you're gonna need a few variables that aren't included in kind of that proving process, mainly a recipient, so what address are you sending this to? And then there's also a relayer and a fee. So the relayer and the fee, with Tornado Cash, as you can bet, like maybe you don't want to, run a function to go claim your ETH, because then people might be able to see that you claimed it with, even if you're sending it to somebody else, you
got to claim it with a wallet that has gas in it.
exactly.
Then how do you get the gas?
Right. So what you can use is called a relayer, and say that you'll pay them a fee. So you can say, hey, I'll pay you 1% of it if you pull it out to my address.
Right.
And that works. And that's actually included in the proof as well. So it's super cool because it allows you to have somebody else that has gas in their account pull it out for you. A lot of regulatory issues around being the relayer,
Right.
obviously,
Right.
but fun stuff. Okay, so now we'll get into the code and just go down it. Require that the fee has to be less than the amount. That's easy. Require that nullifier hashes whenever you spend it, so it keeps track of these nullifier hashes, because at the end of this, what it's going to do is say that the nullifier hash has already been sent out, so you can't claim twice. Basically, this is what it's saying. You can't go back and claim. Another one is it's going to say is known root. So this is going to look in that Merkle tree for that root. And basically, it's just going to make sure that, hey, is your root in our Merkle tree? Like, that's just sort of a sanity check to begin with. And so once those two pass, that, okay, now there's the known root and the nullifier hash, then we're going to do verify proof, which we'll get to at the end. So we're going to skip over this for now, just because that's the whole magic of the Circom files. But what you'll need is it obviously passes all that stuff into that function. And then what it's going to do at the end is set nullifier hash equal to true, so you can't withdraw again. And then it's going to process withdraw, meaning it's going to send out the money to the recipient and the relayer. And that's it. At the end here, there's two functions, is spent and is spent array. You can call and check on nullifier hashes to see if the person has already claimed them. Cool. I mean, that's it. That's the Tornado Cash code. It's super simple, super special. But what is this? And let's kind of get into it a little bit here. Okay. So first, I'm going to run. After you've npm-i'd in your library, now you can run npm run. Okay, so let's see what build does. Okay, so build is actually going to create a whole bunch of files, and it's going to take a long time. But we'll kind of get into it. And what it's doing is it's making all of these elliptic curves and zero knowledge things and making it work, and it's creating your verifier.sol file, which you're going to use and which we'll get into. But what are Circom files? So Circom files are the things that you're going to compile down into your verifier.sol. For Tornado Cash, the main one is called withdraw.circom. And we'll just kind of walk through it. They're actually not that hard to read. You'll see the verifier is the weird mathy thing that you have to read. Writing Circom isn't that difficult. It's difficult in the sense that there's like very limited error messages, and there's not even color coding on the files yet, because it's just a super new language. But it's actually not that bad to pay attention to. So we'll walk down. You can see. Okay, so on withdraw, what do we need here? Okay, so it's going to include a few libraries from Poseidon.circom. So these are like the hasher libraries that the Circom library people make for you. But what's going to happen is you're going to need these inputs are what you actually need to input in. So if you remember back from our Tornado piece, we have some inputs. We have the proof, and then the root, nullifier hash, recipient, relayer, fee. And so whenever you come over to the withdrawal, you'll see the root, you need to input it, the nullifier hash, recipient, relayer, and fee. You can see they actually don't take part in any computations, they're just there. I want to ask somebody from Tornado Cash why that is. Like maybe it's just like if you add more things, it confuses people. But I actually don't know why they put it in. It's not taking part in any computation. And then what you're also going to need to put in, so you can tell at the end here when it says component main public. So which ones are public? The root, the nullifier hash, the recipient, relayer, and fee. And you're going to remember these are public ones. So people can see these whenever they're inputting it. But the rest of the private ones are all handled via the proof. So the private ones, you're just going to calculate a proof that you know them, not necessarily show them to anybody. And that's where the zero knowledge stuff comes in. So which one, what do you need as far as the private ones? And you need the nullifier and the path elements. So the nullifier, so what's it going to ask you? The nullifier, basically, the nullifier that you used in your earlier commitment, it's going to make sure that that matches the nullifier hash that you put in publicly. So therefore, you need that. And then it's also going to need those path elements and path indices. Those are the locations on your Merkle tree. So that way you can prove that, hey, given these paths in this Merkle tree, I can prove that mine is somewhere in there. And that's what you sort of need for inputs. We can walk through, I mean, we can even walk through the Tornado Core one. I mean, now we're on a slightly different one because they updated it. Because like here, they actually bring in the secret too. So we'll use the real ones. So you can see the other ones are the exact same. I thought they looked different. So you're bringing in the secret, the nullifier hash, and then what you're doing is you're making, you're checking here, this triple equal sign, make sure that the nullifier hash, that this hasher, so this hasher as in like the Circom hasher matches the one that you put in publicly. That way you can't be lying about it. So it's going to hash the secret and the nullifier on its own, and then calculate out the hash and make sure they're matching. So that proves that you know the secret and that you know the nullifier. Now let's get on to Merkle tree checker. Merkle tree checker is basically, it's going to go over to this Circom file, which is, this is a Merkle tree built in Circom. And we'll just kind of skim through this. But basically it's going to check that on your leaf. So the far one, so the commitment that you put, so you remember Spuddy's commitment at that far root, that's your commitment, and then that the root is equal to your root. So the one that you're pointing to is equal to the one that you want it to be. And then here, it's going to put in all of these. So it's going to make sure that the elements are all the same so that the tree that you're trying to claim from is in fact all valid. And that's about it. These other ones aren't used in anything. Oh, here we go. Yeah, add hidden signals to make sure that tampering with recipient or fee will invalidate the snark proof. There you go. There you go. I answered my own question by reading the contracts, actually. So don't do that. Better stay on the safe side. So yes, purely mathematical. So basically they're making sure that you don't mess with it actually in the code, which is cool. Cool, we all learned something today. Okay, so back to Tornado. What happens, so after we ran, if you saw npm run build is done, so we'll actually go up now to our Poseidon library and we'll come to the verifier contracts. And this was created by the Circom library people. So whenever you run, we can see the command here in the package. So you run npm run compile circuits, and then it runs this quick setup script here. which has like npx snark.js, prepare, and it's all these phases of zero knowledge proofs. And what it's going to do is it's ending with building this verifier solidity file. And this is the verifier. You'll see, I'm not even going to attempt to walk you guys through this because it's a whole bunch of math that's above my head. At some point, hopefully I can get into it. But the only public function in here is the one at the very end, which is verify proof. This is the one that you call from your smart contract library, and it needs your proof, and then it verifies that all of those private inputs and public inputs that you had in there were valid, and then it will either return true or false. And that's sort of the magic of it. So it generates all of those numbers up there based upon the keys and the inputs, and then will return true somehow. Right now it's still magic to me, but I'm sure there's somebody like Jordy Boline out there who wrote this that can explain to you how it actually works. Okay, so now I think that was about it for the solidity code. What you can see too, so if you want to use it via scripts, how would you do that? So if you come down to Tornado Core, there actually is a nice library down here called cli.js. So this is like the client you can run, like creating a deposit. So if you wanted to create a deposit, you need to input a nullifier and a secret. And then, yeah, it just will return to you your deposit, which is kind of cool. You'll see here, like if you deposit, you can even just run deposit a currency and an amount. It creates a nullifier out of a random number and a secret out of a random number. And that's what you need. And then if it'll go through and actually make everything for you. And then it'll spit out all the different things that you need to know, which is super cool. So same here, generate Merkle proof. So you got your deposit up there. All you do is you run generate Merkle proof. It'll sort of do the deposit, and then it'll get, so it returns to you that commitment that you're going to need. And then it makes a new Merkle tree, grabs all the leaves from it, all the things that you need to input, and it'll return to you those little things that you need down here at the end, your root, your path elements, and your path indices. So it's sort of cool. They've done a lot of work, made it work. So kudos to them. Anyway, hopefully you guys can still hear me. I just realized I'm like behind the mic. Mike, could you hear me just fine?
Yeah, you sound great.
Anyway, I guess not. We'll see. Anyway, that's it. Thank you for listening. We'll see what you guys think of that. Hopefully it was okay. If you have any questions, happy to kind of answer it. And yeah,
What Mike says.
hope this helps. So thanks.